All right. Yeah, so I'm Matt Mecklenburg. I'm the managing director of the EICN. That's the Electron Imaging Center for Nanomachines. And we're going to talk about what electron microscopy can do and what it can do for you. Okay, so we have some fun facts here. So fact one, electron microscopes can see atoms. They're one of the few tools that can see atoms, especially in 3 dimensions. Fact two, transmission electron microscopes are used to measure transistors in your phone. Every semiconductor fab out there in the world will have a bank of electron microscopes, and they'll have people like me that sit there all day and just look at different cross sections of transistors that come out of wafers. So you take a big 12-inch wafer that's coming off the assembly line, and they can actually pluck out individual transistors and say, hey, how big is this one? What is the size of this one compared to this one on the chip? And actually see how well they're doing. If there's a fault in the machinery, if there's a fault in the process of actually making these transistors, they can actually see the individual point and actually pull out that defect and actually do some post-mortem on the process. Fact three, transmission electron microscopes are the only tool that can directly image proteins and viruses at the atomic level. So like when you have proteins and viruses that cannot form crystalline structures, the only thing you can do is put them in a transmission electron microscope. And this is why places like NIH and other facilities that are interested in health, places like Amgen, will use electron microscopes extensively to image proteins and viruses. They actually have data banks of proteins and various other structures that they've identified that they use for the study of drug development. An example of an image of a virus is shown here up at the upper right corner, and you can see all the different spike proteins on top of this virus, and it's been colorized here. They're all actually not a particular color, but it's been colorized here to see the different features within that virus. Just below that, you can actually see a gold nanoparticle in the individual atoms, atomic columns inside of that gold nanoparticle. So those individual columns are separated by about 2 angstroms. The lattice spacings in most crystals are somewhere between 1 and 3 angstroms, so this is a good representation of this ordered little crystal here. Okay, fact 4, electron microscopes have electrons are traveling close to the speed of light. So this is a really fun fact that the electrons in the electron microscope are traveling somewhere between half the speed of light to 3/4 the speed of light, depending on the microscope. And so our old friend Albert Einstein gets to feel very proud that all the features of relativistic change are put into these microscopes every single day. So if you ever asked what the purpose of basic research is, well, the purpose of basic research can be that 100 years later, your crazy ideas actually go into a tool that helps understand transistors, and helps understand viruses every single day. Okay. Fact 5, electron microscopes use magnets 40,000 times more powerful than the Earth's magnetic field. We have these really big 2 Tesla magnets. And yes, Tesla actually refers to magnetic fields, nothing electric like in the car. The 2 Tesla magnets that go inside of these microscopes that actually steer the electrons down. They go through from an electron gun. They get sped up to about 3/4 the speed of light. They go through all these different lenses. They go through the sample. This quantum mechanical wave of the electrons actually travels through the sample, gets phase shifted, and then interferes to form an image, and that's what we look at. So this is another example of fundamental quantum mechanics coming in 100 years later and producing these wonderful tools that we use every single day. And then we actually have wavelengths that are about 250,000 times smaller than that of visible light. The wavelengths inside an electron microscope are about 2 picometers in size. Optical microscopes are wavelength limited, so they can actually see the size of things that are on the order of the wavelength, so about 500 nanometers, or a little bit better if you have super resolution. But electron microscopes have wavelengths that are about 2 picometers. Can we see things at the 2 picometer scale? Absolutely not. Okay, I wish we could. We cannot in any way, in any form, see anything at the 2 picometer scale. These kind of images here are roughly about the state of the art, but somewhere between 50 picometers and 200 picometers. And we're limited to that scale because electron microscopes have terrible aberrations in their lenses. Okay, terrible aberrations. If an electron microscope was a person, it would be legally blind. Okay, just absolutely terrible aberrations. And we use tiny little aberration correctors to make it a little bit better. But because we cannot, in optical things, you can machine down to 1/10 the wavelength and make it basically perfect. We cannot machine down to 1/10 of a picometer in order to actually see down there and actually get the aberrations free and work at that scale. So yeah, electron microscopes can do all kinds of cool things. Here's another example of a virus. This is a little capsid that's absolutely enormous. This capsid is about 120 nanometers across. And you can actually see cool details like this little portal where all the DNA comes in and out of or goes out of the capsid here. You can use these electron microscopes to see the individual walls of a carbon nanotube. So that's what we have at the upper right. And those walls are about 3.4 angstroms in size. And you can actually, even though this carbon is very, very sensitive to the beam, we can actually image at that level. Here's another example of a gold nanoparticle imaged at atomic scale. All of these things are possible with the different microscopes that we have. We can do cool different things, like we can look at the RNA editing machinery, so you can actually see the different components that make up this machine here, and you can actually see you can actually identify the protein that's doing the editing. That's what's shown in magenta there. When we do tomography, we can actually see inside of these objects in 3 dimensions. These objects can't really form crystals that well, so this is the only technique to look at this at really high resolution. And in the capsid we showed earlier, we had removed all the DNA, but you can actually see inside of this capsid here all these little noodles that are actually the DNA that's like trapped inside of that little virus. Here's an example from the semiconductor side where you can actually see the structure inside of a quantum well. So you can see the difference between the germanium quantum well layer and the 2 semiconductor layers on either end of that. You can actually see the interface nearly at atomic resolution. This particular image here is more limited by the sample than it is by the actual imaging conditions, but you can actually see that atomically sharp interface from the epitaxially grown layers really quite well. So I'd like to introduce our team. You might recognize one of these people. But then we have Ivo, Wang Hui, Hongzhou, our founding director, David Strugatsky, and Judy Su. And we have a really, really great team. And they're absolutely available to help for both assisted usage and if you want to get trained on any of the tools in any way that you want to understand them. And then I'd like to introduce the instruments that we have. So we have, in this picture, we have two pictured SEMs. One is coming soon, and we can show you where it's going to get installed. And then we have 5 TEMs shown here. The TEMs, basically all the data that I showed you so far from the transmission electron microscopes. The 5 TEMs here is missing one important one, which we'll talk about in a moment. But each one of these microscopes is at a different level of performance. And so you start at like the introductory microscope, the T12. You understand the basics of microscopy, and you move up to the more advanced tools, and then even to the really powerhouse tools that get you down to like atomic resolution on a routine scale. The one thing that's missing is our Cryo's G4. This is now in the building, and it is up and running. It doesn't look like much from the outside. It looks like a box. We can show you, and it has this beautiful blue light. But on the inside, it has all these kind of cool tools. Now, what's really, really interesting about this microscope is that this G4 in this configuration is the first one in academia in the United States. There are a couple at, there's one in a national lab, and there's a couple at pharma. But basically, this microscope has been designed to build on the resolution revolution that's going on in structural biology. And it is designed to do really, really high throughput, real-time structure determination of these viruses and proteins that we're talking about that are so fundamentally important to human health. And so it's got all kinds of tools that I can go into associated with that make it this really, really, really powerful tool. And we're really excited to work with people to basically output as much as we can, learning about both human health and the huge expanse of proteins and other structures that are in the biological space that don't get examined because human health takes such a huge priority. Any questions? No questions? Did I talk fast enough? Okay. All right, cool.